Let's see dispersion. You already have a little bit of idea of light, white light splitting into its component colors when it passes from a prism. We're going to see why that happens, and then we'll define certain things. Look here. We have a prism. Angle of prism is A. We used to define refractive index of the prism as mu, and then we take a white light it goes like this and then comes out like this. Now, if it's a white light, white means all the colors are present, then once it enters into this prism, its behavior will be different. And why will that behavior be different? For that, you must understand origin of mu. What was the origin of mu? Snell's law. That was sin I upon sin R. This ratio was a constant, and this constant was called refractive index of the material. Now, refractive index of the material was also defined in this way: speed of light in air divided by speed of light in medium. That's how we define refractive index mu of a medium with respect to air. Now what happens? White light is basically collection of violet, indigo, blue, green, yellow, orange and red with gear. White light is what? Violet, indigo, blue, green, yellow, orange and red. Now, what do you mean by these colors? When you say color, it means frequency. Different frequencies are perceived by our brain in the form of different colors. They all are electromagnetic waves. These electromagnetic waves are what? Electric field oscillations and magnetic field oscillations. So when electric field oscillates with a particular frequency, let's say you define that violet color. You change the frequency, it becomes indigo. You are observing same electric field, but oscillation is different. A simple example, a simple way of understanding is that, suppose for the time being, if 100 oscillations per second, somebody says that this is violet, 100. If you make it 90, it becomes indigo. If you make it 80, it becomes blue. It's not 100 oscillations per second, it's much higher than that. We'll see that later. But as of now, an electric field oscillating at a given frequency is observed by a human brain in the form of a color. Just like variation of sound with a given frequency, you call that what? Sound basically. And what is that which is oscillating? Pressure, change in pressure. The change in pressure is interpreted by the brain as what? A sound wave. Similarly, electric field oscillation, rate of variation is called color. Now, in this wave gear, I hope you know that as you move from red to violet, frequency, let's represent it with nu, it increases. As you move from red to violet, frequency of color increases. This frequency, which you say is increasing, if you consider a wave traveling from air into glass, we say that frequency does not change, but frequency is increasing. Frequency does not change. What is the meaning? If red light is entering into the prism, then its frequency will remain same. Suppose frequency of red is 10, 10, 10, 10. If frequency of orange is 20, 20, 20, 20. At times लोग कंफ्यूज हो जाते हैं कि फ्रीक्वेंसी चेंज होती है या फ्रीक्वेंसी चेंज नहीं होती है. Frequency part of different colors is different. That is different. But as you move from one medium into another, frequency of a given color, it does not change. First of all, write down this statement. Electromagnetic waves in visible spectrum are perceived by human brain in the form of different colors, and frequency increases as we move from red color to violet color. And frequency increases as we move from red color to violet color. Now, next line. When a wave travels from one medium into another, its frequency does not change. When a wave travels from one medium into another, its frequency does not change. That is, if red color enters into a prism, then inside the prism and outside the prism, its frequency will remain same. Then inside the prism and outside the prism, its frequency will remain same. Now, what is the meaning of this frequency and all? Now look here. You know that V is defined as F lambda. Everybody has seen this formula, velocity of wave, frequency, wavelength. In here, we are using c for the speed of light. For frequency, we are using nu, and this is lambda only. Now look at this part. Sin I upon sin r, which is Ca divided by Cm. Ca, speed of light in air or vacuum. All these colors, when they are in vacuum, they travel with same speed, which you know as 3 into 10 to the power 8 meters per second. All these colors, when they travel in vacuum or air, they travel with same speed of 3 into 10 to the power 8 meters per second, which we have taken as what? Ca. But the moment you enter in a medium, this frequency part remains same, but c, it changes. Speed of light. If you have a denser medium, speed of light decreases, and that decrease in light also corresponds to frequency of the color. This part will make mu different. Now will it make mu different? You will understand it in this setup. So when you move from this side to this side, frequency increases. But what happens with speed of light? These colors, let's go into a bit of basics. I told you that these are what? Different frequencies. Different frequencies, you have little bit of idea of photons and all. These photons, once they enter, they interact with the atoms of the prism. Now, once they interact, if they have less energy, less frequency means less energy. If they have less energy, then their chances of interaction with the atoms are also very less. And if you have very high energy photon, then chances of it being interacting with the material atoms, that chance increases. And therefore, if it interacts more with the medium, that slows down the photon of the violet color. If it interacts less, then chances as they decrease, it can go through the material in much faster way. That means it increases the speed of red color, this less interaction. So what basically is happening, you have two, let's say two students are there. One is highly energetic guy and the other one is kind of more dull. And they go in a meeting in a crowded place, let's say a hall, and they have to enter from one gate and then they have to exit from the other across the room. Now the highly energetic one, he will have more friends when he comes out because of many interaction with all these friends. Once he comes out, you will find that he has taken a longer time. Somebody who is looking at this room from the outside, he will find that the energetic guy has taken much longer to cross the room. And therefore, you will say that speed of the highly energetic guy is quite less. On the other hand, if you consider red, the person who is less energetic, he's got few friends, and when he passes the room, there are less interactions. He can come out quickly, and therefore somebody from the outside finds that his travel time is less, his speed is more. And therefore, as you move from red to violet, your velocity decreases, and that is represented by this. As you move in this direction, C, speed of light for a particular color, it increases. Speed of light for violet color is minimum. Speed of light for red color is maximum because of very small number of interaction with the material. Now, once you define your C in this form, now you can see that numerator is what? Speed of light in air, which is same for all the colors. Air means vacuum. If you are in vacuum, if in that room nobody is there, then all these colors, they do not interact at all, and therefore they all travel with what? Same speed. In vacuum, all the colors, they travel with same speed. But the moment you enter inside a medium, if you talk about violet color, then you will be using CV. If somebody is using red color, then he will be using what? CR. C in a medium of what? These colors. So if somebody is dealing with violet color, he will be using speed of light in violet color. Somebody dealing with red color, he will have to use speed of light in red color. Now CV and CR, they are not same in a medium. CV, speed of light in violet, is less than that in red. So if CV is less, you can see that this is less, and therefore the ratio CA upon CV, it will increase. And therefore again, as you move in this direction, your mu also increases. As you move in this direction, refractive index increases. Refractive index of violet color is greater than that of red color, and this is the increasing order. This is something you need to understand. Once we have the idea of mu decides what? R. Sin I upon sin R. Why mu decides R? If I draw a normal at this point, that's a normal. This is white light. This is white light. That means all the color right now, the angle of incidence I is same. All these colors, I is same. For all these colors, mu is different, and therefore R must be different. And therefore, instead of coming out, or once it comes out in the glass, instead of having a single ray, you find that light ray splits into 7 components. It splits into 7 components. 1, 2, 3, 4, 5, 6, 7. These 7 components, finally when they emerge out like this, you see them, and this is called dispersion. Splitting of light into its component colors is called dispersion. Why it happens? Because I is same, mu is different, and therefore R is different. Now, which one is blue, which one is violet, and which one is red? We can also decide that with the help of this setup. Sin I upon sin R is what? Mu. We are interested in sin R, and therefore let's write down sin R. Sin R is coming sin I divided by mu. Now, numerator is same for all these colors. If you increase mu, then this sin R must decrease. If sin R decreases, that means your R decreases. That means if in this direction mu is increasing, then the other direction your R will increase. So this is the direction in which your angle of refraction increases. For violet is the least. For red, it's the maximum. That means, look at this and look at this. Let's draw a separate figure here. If I draw a prism, and let's only take violet and red, then as this light enters, white light, let's only show 2 colors. All the other colors will be in between. It emerges out like this. That's the normal. Now, what is the angle of refraction? Angle of refraction is angle which these refracted rays make with the normal. This and this. Now, we know that R for violet is the minimum and therefore it represents RV. R for the red color is maximum and therefore this one is R for the red color. Which means when you look at this figure, you can write Vibgyor in this form. As a trick, you can remember that when white light enters, comes out in the medium of glass and ultimately comes out in the same medium, surrounding medium, sequence is this. From bottom to top, write down what? Vibgyor. But ultimately, you should realize this part. Now, go down this much, but before that, write down few statements. All the colors, when they move in vacuum, they travel with same speed, which is 3 into 10 to the power 8 meters per second, which is 3 into 10 to the power 8 meters per second. And as light enters into a medium, all these colors move with different velocities. All these colors move with different velocities. With velocity of violet color being minimum and that of red being maximum. Because of this, refractive index of a medium for different colors is also different. And therefore, when white light enters into a prism, angle of refraction for different colors is different. Creating splitting of white light into its components. Now write down from the next line. Splitting of white light into its component colors. Splitting of white light into its component colors is called dispersion. Either CA upon CV or CA upon CR. This is just for your understanding. Note down this much. We have seen why dispersion takes place. Then comes angular dispersion. Angular dispersion theta. This is the prism. Angle of prism is A. White light enters into the prism. Let's consider these two, violet and red only. And as it finally comes out, you know that all the colors are present in this region. Now this region, in terms of angle, is called angular dispersion. What is this region? Look here. This is the original path of white light, which is this. That's the original path. And from the original path, V and R, they have deviated by this much delta R and this much. Delta V. From the original path, these two colors have deviated delta R and delta V. Delta V and delta R, look here. This is the original path, and if this is the original path, we are saying is, let's say this is delta R. This is delta V. Delta V, delta R. Let's say they are starting from the same point because we are interested in the angle only. These rays, when they finally emerge out, all the colors are present in this angular region. This angular region is called angular dispersion theta, which is something like this. You found that violet color is coming out like this, red is coming out like this. So you've got two arrows, two vectors. What is the angle between the vectors? For angle between the vectors, you join them with their tails. This angle is called angular dispersion. All the colors are present in this angular region only. Now, what's the value of delta? We calculated delta as A times mu minus 1. But this was an approximation, and that too for minimum deviation. But if angles are small, then we can say that all these deviations are almost same. And therefore, although these are not minimum deviations, we can still take delta as A times mu minus 1 because of small angles. If delta is A times mu minus 1, what is delta for violet color? A is angle of prism, that is same, and you know that mu is not same, and therefore you will be writing mu v minus 1. Similarly, for delta r, we will write A times mu minus 1 and mu of what? Red color. Now look at this figure. This much is delta R. This whole thing is what? Delta V. And therefore, theta, which is angular dispersion, is delta V minus delta R, which is coming as, if you subtract these, you get A times mu V minus mu R. That's your angular dispersion. A times mu V minus mu R. And one more thing, if you look at this delta and mu for red color is what? Maximum. We can figure out why this should be violet color and why this should be red color. As you increase mu, your delta should also increase. And therefore, as you move from this side to this side, mu increases. For violet, therefore, deviation should also be maximum. For violet, therefore, deviation is what? Maximum. This is angular dispersion. After angular dispersion, we define another term which is called dispersive power. What is dispersive power? We'll see that, but first note down this much. Let's see what dispersive power is. Dispersive power omega. Dispersive power is defined as ratio of angular dispersion and deviation for mean color. Write down the statement. Dispersive power omega is ratio of angular dispersion and mean color angular deviation. Mean color angular deviation. Now, what are angular deviations? Deltas. What is the mean color? Mean color is taken as yellow normally, and therefore we define omega as theta upon delta yellow. Out of all these colors we pure, yellow is considered what? Mean color. And for that mean color, angular deviation is what? Delta y. That gives you omega as theta upon delta y. Now, what is theta? We have already calculated that A times mu v minus mu r. A times mu v minus mu r divided by delta for mean color, which is A times mu y minus 1. A and A cancelled, and this is coming mu v minus mu r divided by mu y minus 1. This dispersive power term is obtained just to remove A. Now you can see that dispersive power has nothing to do with angle of prism. Angular dispersion, it depends on angle of prism. But dispersive power is something which is independent of angle of prism. It only depends on the medium. For different prisms, of glass, same type of glass, your omega will be same. If you take angle 30 or 60 or anything, your omega will what? Remain same. This omega, therefore we say, is the property of material of the prism. It has nothing to do with shape, that means angle of prism. Write down the statement. Dispersive power does not depend upon angle of prism. It only depends upon material of the prism. It only depends upon material of the prism. Now, they will ask you a simple question like this. What is dispersive power of a glass slab? Dispersive power of a glass slab. And what is angular dispersion for a glass slab? If it's given that for the prism with angle 60 degrees, for a prism with angle 60 degrees, they gave you that, say omega is 2 for the prism, and angular dispersion for this prism, suppose this theta is coming 20 degrees. Let's take these random values. The question is that for a glass prism, theta is 20 and dispersive power is 2. Then for a glass slab of same material, what is omega and what is theta? Then you will say that for same material, dispersive power remains same, and therefore omega for the prism is also what? 2. And what about theta? If this angle is A, the angle A is between these two faces. If these two faces, they become parallel. And what is the angle between parallel faces? 0. If A is 0, then what is theta? 0. And therefore, for a glass slab, theta becomes what? 0. For a glass slab, it's not about glass, for any parallel face medium, angular dispersion will be what? 0. What does it mean? It means this, which you have already visualized in your life. When white light, it falls and interacts with this face as it ultimately comes out, you all have seen this splitting of light. But in your windows, you use glass slabs. And when light passes from that glass slab, when light passes and enters into that glass slab, it should split like this. But ultimately, when it comes out, you do not see any coloring. What is the reason? theta is what? 0. That means if white light comes and interacts with this glass slab, as it comes out, you will again see what? White light. Now, this is something which is very interesting. How come this is interesting? First note down this and then we'll understand basic meaning of this theta so that you understand why a glass slab does not show any color, although I told you that this splitting is happening. First note down this much. Now look why you do not see splitting of white light into its components when you have a glass slab. This is your glass slab. This is white light. And as it comes and enters into this glass slab, you know that you will see different colors, V and R. This is the normal. Now which one is V and which one is R? Closer to the normal is what? V. Further away you will get R. And ultimately as they move out, emerge out, they will come like this. Look at this setup. I hope you can see that these two, they both are parallel. This is your V, this is your R. Inside, they're not parallel. Inside, they're not parallel. As they come out, V and R, they become parallel. Why? If you remember this format, mu, sine, theta, it was constant. Mu sine theta, or you can remember it like this, mu n sine in, what? Constant. So this medium is air, mu, air. This medium, air. And therefore, for these two mediums, if you are having parallel faces, then this I will also be same. We have done a question in refraction. Very first lecture of refraction, we have already done something like this. The product of mu and sine of angle in that medium is always a constant, provided these faces are parallel. You can have different mediums which are parallel to each other. In any medium, when light enters, refractive index of that medium, its product with sine of angle which light makes with the normal in that medium, that product always remains what? Constant. This is air, and therefore as light finally comes out, this, if you say that that's a normal, this is another normal. If you say that this angle is, let's say, alpha, then this is also alpha and this is also alpha. They will remain what? Same. Now once you found that both V and R, they make same angles, alpha and alpha, immediately you know that theta is what? 0. What is theta? Theta is angle between these two rays. That is 0. Now, one would expect that in a situation like this, he should see violet and red in this form, which is basically what? Splitting of light. You must see all the colors between V and R. But this is something which doesn't happen. If white light enters, you know that white light comes out. So what basically theta 0 means? Why does it happen that you see a white light, although figure says you should see splitting of it into its components? Pause the video, think about it, and ultimately, if you find that your guess is same as the reasoning which I gave, then that is not a guess. Look here. Now this is the white light and you get R and V. But this is not the only white light. This is not the only white light. What is happening? There is some other ray which is also moving parallel to this one. You don't have a single beam, only one ray. It is a collection. There are several rays which are coming. If you somehow can create only a single beam, only a thin ray, only one photon, then you will see the kind of splitting I've talked about. But in reality, this light is coming as a big cross-section beam, and when it falls, this thing again splits into what? V and R. V and R. So when it splits into V and R, when it splits into V and R, look what we have done. This is V of this second ray, that's the V. This is R, this is R, this is R, this is R. Let me show this thing with blue color. This is V of this second incident ray. And this is the R, this is the R of the second incident ray. And therefore, this is your R. Now, these two are parallel. That means for the second ray also, angle from the normal is what? Alpha. And therefore, as they come out, all these angles, they are what? Alpha only. Now, for the second one, R coincides with what? Violet. Third one, fourth one, fifth one, there are millions and trillions of these rays coming, and therefore what happens? At every location, you have superposition of all these colors. But since you have parallel faces, which means theta is 0, which means all the colors as they emerge out, they are parallel. That means finally at this point, you don't see a single red, you see a superposition of VIV, GYOR. These VIV, GYOR are of different rays. But as they finally superimpose, you get what? White light. So when light ultimately comes out from this region, you see white. When it comes out from this, you see white. When it comes out from the light comes out from this, you again see what? White. But if you have a prism, then in that prism, because of the presence of A, since A is not 0, theta is also not 0. That means what? This is a ray. Ultimately, you found V and R. But this V and this R, they are not parallel. Theta is not 0. That means if somebody takes a second ray, for that second ray, third ray, fourth ray, fifth ray, all these rays, some other ray, its component color, let's say R, is present here. If R is present here, then it will not be moving in this direction. That R moving in this direction only, parallel to this R, parallel to this, of some other color or of some other ray. When you take component of its colors and all, then you find what? R also emerges out from this position. Now, this R and this R, they are parallel. Why? Because for this and this, refractive index is what? Same. Angle of incidence is same. Angle of incidence is same. Refractive index, it depends on color, that is also same. And therefore, angle of refraction at this place and ultimately at this place, they are also same. And therefore, all these red, they are parallel. But they are not parallel to the violet color. All the violets, they come out, all the violet, you will find they all are parallel like this. This is violet color of some other ray. When it comes out from this point, R, V and all the colors in between, they are no longer parallel. And if they are no longer parallel, that means you cannot superimpose all these waves together. Which means you will see what? Splitting of light into its components. I hope you understand why a prism shows dispersion, but a glass slab, it does not. If you can somehow enter inside this medium, inside this, then what will happen? That's my question to you. Think about it. If somebody enters into this medium, not in air, over here, then will you see splitting of light into its component? Will you see dispersion like this, or there will be no dispersion? Think about it. That's your homework. Or down this much. Same medium on both sides. Glass slab, you can take any medium.